let's define two operations on vectors. Let u and v be vectors so that u is u1, u2, u3, and v is v1, v2, v3. We define the sum of two vectors, u plus v, to be the sum of each of their components. Sometimes when I'm teaching this in a pre-cal class, before we add vectors, and in that pre-cal class we're only adding vectors in the plane, I just write two vectors on the board and say add them. No instruction, just see what the students do, and they always come up with this rule on their own. The nice thing about adding two vectors is it's exactly the way we think about it, right? We would make this rule up. It's also good to note that this looks like a rule for a vector in 3 space, but if you cover that last spot up, you have a vector in the plane, a rule for vectors in the plane. Well, anytime we're talking about vectors in space, if I let the last coordinate be 0, well, then in a right-handed coordinate system, if I had x and y in the plane, then my z-axis coming straight up at the camera. Well, if I let those last coordinates be 0, then I just have vectors in the plane. So anytime I have a rule for a vector in space, it's automatically a rule for a vector in the plane. Okay, so we add two vectors together by adding them up component-wise. For scalar multiplication, right, we're going to multiply a vector by a scalar. So let k be a real number, any scalar. Then k times the vector u is simply k times u1, comma k times u2, comma k times u3. We simply imagine distributing that constant through our vector. So let's do a couple of examples. In our first example, we're also going to come up with another way of thinking about vector addition. So for this example, I have two vectors in the plane. U is the vector 1, 5 sketched here, v is the vector 3, 1 sketched here, and I want to write down u plus v. All right, well, not too hard, right? The vector u plus v is 4, 6. So if the instructions were just add the two vectors together, I've done it, but I want to sketch that new vector in. And so here is the vector u plus v in standard position. Right, and something feels good about this, right? If I thought about u and v as forces, right, tugging on an object in two different directions, well, the object would end up moving along that direction, right? U's tugging a little harder than v, and we end up with a force vector in the middle. But what's even better than that is I remember that I can draw these vectors basically anywhere in the plane I want as equal vectors, right? Because they just have to have the same direction and the same length. So if I start at any point in the plane and go over 3 and up 1, then I've drawn vector v. So I want to imagine doing that from the terminal point of view. So over 1, 2, 3, and up 1, well, I end up at the terminal point of u plus v. Well, if I think about that, that was the point 1, 5, and if I go over 3 and up 1, now it's the point 4, 6. Well, order in addition doesn't matter, right? 1 and 3 make 4, 3 and 1 make 4. So I could start at the end of v and go over 1 and up 5 to get to that point as well. And so what I see now is this vector u plus v on the inside of a parallelogram, where all of the sides of that parallelogram are the vectors u and v. This is called the parallelogram law. For adding vectors, the sum of u plus v is always that long diagonal in that parallelogram spanned by u and v. So that's a nice thing. The vector u plus v is also called the resultant vector. So while we have these vectors here and we have that nice parallelogram, let's do one more example. Let's find u minus v. And right away, it's kind of like, well, I had a rule for u plus v. We didn't actually write down a rule for u minus v. So I'll think about this as addition this one time. Though I will say, if you just go on and subtract the two vectors the way you normally would think about subtraction, you will get it right. But u minus v should be the same thing as u plus minus 1 times v. Well, I do have a rule for multiplying a vector by a scalar, and then I have a rule for addition. So subtraction is going to work out the way we would make it up to. But if I think about minus 1 times v, well, that would be minus 1 times 3 comma 1. Imagine distributing that minus 1 through, and I would get minus 3 comma minus 1. So the vector u minus v would be 1 plus a minus 3, minus 2, comma 5 plus a minus 1. So let's sketch that vector in. All right, so there is my vector u minus v, and right now it's like I'm a little disappointed. I was hoping that vector would show up in my parallelogram, right? Because my parallelogram law contains the resultant vector. It'd be nice if it contained this difference of two vectors too. And then I remember this nice thing, right? I can add vectors in either order, right? U plus minus 1 times v, I could swap that order, right? Or I could simply think about what minus v is, right? Well, minus 3 minus 1, 1, 2, 3, it's v, but going in the opposite direction, right? If I just shifted that vector back there, it literally just going down the other direction. So u plus minus 1 times v. Well, here's a vector u, and minus v would simply go the other direction, right? Minus v is that dotted vector I just drew in going backwards. So u plus minus v gets me to that point right there. So I claim that this vector that I would draw from the terminal point of v to the terminal point of u is u minus v. And I can actually see very nicely that it really is u minus v. The other thing I could do is I could go this way 2 and up 4 to see that I really do get to that point. So in my parallelogram now, I see the resultant vector u plus v, and I also see the difference of two vectors, u minus v. So I want to sketch in the parallelogram law here, just imagining any two vectors. So I had a vector u and some other vector v, and this time I'll draw v to be the longer vector just for the heck of it. I can sketch in the vector u plus v by drawing a copy of u. So just a vector parallel in the same length as that vector u. And then I draw another copy of vector v starting here. The parallelogram law tells me that u plus v is this diagonal. And that u minus v is this one. Okay, let's do one more example, but this time just thinking about scalar multiplication. So let's just make up a vector and then multiply it by a constant. We've already multiplied a vector by minus 1, and we saw that it changed the direction, right? What I would say exactly the opposite. So let's just do something different this time. So let's deal with another plane vector. And let's let it be minus 2 comma, well, 4. We just saw minus 2 comma 4. So we'll just let our vector example here be that one. And there's the vector I'm calling u in this example, though it was u minus v a moment ago. So let's imagine multiplying u by 3. Well, that would be the vector minus 6 comma 12. All right, so I need to go over to minus 6. 1, 2, 3, 4, 5, 6, and then up to 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and oops, run out of room here on the board, so we'll just do the best we can. So over 6, 1, 2, 3, 4, 5, 6, and up. That was 11, and so 12 would be something like right there. And so what I see is the vector 3 times u is this vector that even runs off my board. And so I see right away an effect of multiplying a vector by 3 is that it, well, got longer. And in fact, it got 3 times longer. If I find the magnitude of u, well, I would get 4 plus 16 is the square root of 20 is 2 times the square root of 5, and we should always reduce under a radical. And so now if I wanted to find the magnitude of 3 times u, well, I would get 36 plus 144 is equal to the square root of 180. Well, right away I see that 180 is 9 times 20, which can actually lead me to, I guess, the better conclusion that 180 is 36 times 5. So I get 6 root 5. I look at these two distances, and 3 times u, really 3 times as long as u. So that lets us kind of conclude something nice. If k is a real number, and v is a vector, the magnitude of k times v is equal to, and I want you to look at the example we just did and see if you can fill in what this should be equal to in terms of the number k and the vector v. And I'll just let you pause the video here for a moment, and then we'll fill in the blank together. Okay, so I have a feeling a number of you might have written down k times the absolute value of v. And I would say that's very close. The one thing we need to be careful about is k can be negative, which would multiply our vector. So maybe I have a vector v that looks like this, and if k is a number bigger than 1, k times v would be longer. But if k were negative, it would flip that around the other direction. Well, magnitudes can't be negative, so I actually need to protect that in an absolute value. So the absolute value of k times the magnitude of v gives me the magnitude of this new vector, k times v. This is actually where we get the word scalar from. When you multiply a vector by a real number, you scale the vector. You make it longer. If k is less than 1, you'd actually shorten the vector. 1/2 times the vector would half the length of the vector. So that's all I wanted to do in this video, but you should find a table in your textbook that is about properties of vector operations. Below the link to this video, you'll see a page number. You should go through those operations and make sure they all make sense, and look at the examples your author does with regard to those operations. So check out those properties of vector operations in your textbook.